right, let's continue our adventure here into vectors. We're going to, first I want to start and kind of recap yesterday, and then we'll continue on in the 6.1 lesson. From yesterday, we learned how to convert a vector that maybe wasn't in component form, but maybe instead was written as two ordered pairs. It's a vector that goes from L to M. Can we turn this into a vector in component form? Remember that your formula for that was to take, basically all you're doing is taking x2 minus x1. I'd have -2 minus -5. And then I'm going to do the same thing with the y's, 6 minus -3. The order that you did that was important to remember because it has to do with the direction that it's going. This component, or this vector p in component form would be 3, 9. That's the first thing. Next thing, could you find the magnitude of that vector? Recall that the magnitude of the vector we notate like this, and it's going to be the square root of a squared, or x squared, that would be 9, plus b squared, or the y squared, that'd be 81, which is then the square root of 90. And you could reduce that and simplify that as well. The next one is find the unit vector in the direction of vector p. Well, I just found out that vector p is the square root of 90 units long. That's almost somewhere between 9 or 10 units long. That's not a unit vector. A unit vector is only 1 unit long. So this is way too long right now, or this vector is way too long. Remember, to find the unit vector, you just take the vector that you have and you divide it by its magnitude, and then you'll get it down to a magnitude of 1. Since it's a unit vector, I like to use a u, and that would end up being 3 over, let's go ahead and reduce this square root of 90 as a 3 root 10. And then I take the y value, the vertical component, 9 divided by 3 root 10. Then I'm going to go ahead and simplify that. That unit vector would end up just being 1 over root 10 and 3 over root 10. That vector is 1 unit long. You can always check it by finding its magnitude. This squared would be 1/10 plus this squared would be 9/10. 1/10 plus 9/10, that's 10/10. That's 1. Square root of 1, 1. All right, last thing. Write this unit vector that I have, write it as the linear combination of the standard unit vectors. Remember, the standard unit vectors are that I and that j, and all you really do is take your horizontal component times vector I plus your vertical component times vector j. Let's look at one more review problem, and then we'll move on to some new stuff. Let's try something new here, or a little bit trickier. This one, it says find a vector in the direction of, and if you were in class, we would have picked somebody to choose a vector such that its magnitude is something that somebody would have chosen. So since I can't hear what you're picking, I'm going to pick
438.
Okay, that's my husband, and we are not going to use 438. Give me an ordered pair, Brian.
You and me?
Help me out here.
I don't even know what an ordered pair is.
I don't even know what an ordered pair is. What am I working with here? Okay, here we go. I'll make it up. It's a vector, -2, I don't know, 5. There we go. There's our vector. So we want to find a vector in the direction of that vector. But we want its magnitude to be different than what it currently is. Let's just keep it simple. We'll make it 10. Now that's not the same as a unit vector, but it's kind of similar with the idea. It's not going to be 1 unit, it's going to have to be 10 units long. Okay, we can do this. It goes in the direction of -2, 5. So -2, 5 is about like right here. But how long is that vector right now? Well, we could figure that out. I'm going to call it vector v. And its magnitude right now is 4 plus 25. It's the square root of 29. The square root of 29 is somewhere between, what? Is this the same number we had earlier? That's a coincidence. Okay. Somewhere between 5 and 6 units long. But I want it to be 10 units long. Even if I doubled it, it wouldn't be exactly right, but that'd be closer to what I want. Okay, here's what we're going to do. When you have a problem that you need a vector to be a specific length like this, what we're going to do is we're going to take that vector and turn it into a unit vector first of all. I'm going to cut that unit or that vector back and only make it 1 unit long. I'm going to make it shorter. Let's start with that. I've already found its magnitude. I'm going to take that vector, -2, 5, and I'm going to multiply it by 1 over root 29 or divide it by root 29, however you want to think of it. And it's now going to be a unit vector when I do that. The unit vector is -2 over root 29, 5 over root 29. Now the length of my vector is only 1 unit. But I want it to be 10 units. What would I need to do to the unit vector to now turn it into 10 units so that there's 10 of these little unit vector guys going along here until that length is 10 units? Well, all you got to do is take the unit vector times 10, right? You're going to take it times, it's 1 unit now. If I multiply it by 10, then it's going to be the right length. So I take that unit vector and take it times 10. That's going to end up -20 over root 29, 50 over root 29. And that is now a vector that is in the same direction as my original, but now it's going to be 10 units long. All you got to do is turn it into a unit vector so that it's 1 unit, and then multiply it by whatever length you want. And you've got it. That's one of the conveniences or one of the reasons that we use these unit vectors. It's kind of a middle point, a middleman to get us to what we really want, which is a specific length. On to the fun stuff. This is where it really gets interesting with these vectors, because we start applying this in some navigational kind of things. Let's talk first of all about direction angles versus bearings. We've been working with what we call directional angles, mostly. We've talked very briefly about bearings in a previous chapter, but most of the time we always think everything in terms of the unit circle. Those are called directional angles. That has to do with the unit circle. That means 0 is on the far right, right here, and you wrap around an angle this way. That's a direction angle. Theta is the angle formed by the vector and the positive x-axis. That's this angle right here. Let's make up a number for that. Let's call it 150 degrees, because that's kind of what it looks like it might be. Now, when you're talking bearings, this is always the angle that's formed by the line of travel, which is our vector, and always due north measured clockwise. We're talking starting due north and coming clockwise. Well, that is not the same as my 150 up here. That's a much bigger angle, though the vectors go in the same direction. Anytime that we are doing math, something on our calculator, we have to use the direction angle. But the problem is that the problem is often given, and we often have to answer in bearings. So this is how we report the direction. We're going to be converting back and forth. Like if they give it to us in bearings, we will have to convert that angle to direction angles so we can do math, and then we have to convert back so we can report the answer back as a bearing. We need to be able to shift back and forth between the two. If you think about this, there's so many different ways. It just depends on how you see this angle right here. I guess how I see it is I look at this as 150, which means this has to be 30 right here. And this all depends on what quadrant you're in, on what you would do. You would do different things depending on where your vector is at. But in this case, I look at this and see this as a 30, which means right here I've got 90, 180, 270, and another 30. That means that in bearings, this angle is 300 degrees. I would use 150 to do math. I would answer with a 300. Be able to convert between those two. Now, we're going to look at the direction angles like we had yesterday and the day before when we had geometric vectors. And the very end of the 6.1.1, which was yesterday's lesson, at the very end, I threw a problem at you like this. And we had to find this. I gave you the angle, I gave you the length, the magnitude, and we had to find this component form. Well, it was just trig. Remember, we wrote right here, this is what we did. We said that the cosine of theta was equal to the adjacent over the hypotenuse. And the hypotenuse was just the magnitude of our vector. So this is what we did right here. And that gave us that was x value. We had to solve for x. So we multiplied both sides by the magnitude, and that found our x, our horizontal component. Well, actually then, this part right here that we did, that we kind of worked through doing our SOHCAHTOA, really boils down to this is always going to be the x value. So we're going to maybe try to bypass all this SOHCAHTOA stuff, and we're going to go straight from, if I need the horizontal component, all I got to do is I got to take the magnitude of my vector, multiply it by the cosine of my angle, and I've got it. Likewise, remember when we were trying to find the vertical component, we were looking for this, we said, oh, well, that would have to be the sine of theta equals opposite over hypotenuse, so that'd be y over the magnitude of my vector, which I had given you at that time. And then you multiply both sides by that magnitude, and that gets your y isolated. That means my vertical component will always end up being the magnitude of your vector times the sine of theta. That is such a nice shortcut. You should remember that because we're going to use this right here instead of working through all this SOHCAHTOA stuff every time. What this means is I could take those geometric vectors that we were drawing out on day one, where I gave you the angle and I gave you the magnitude, and we could very quickly take those two pieces of information and turn them into a vector in component form. That's kind of where we're headed. Let's do one of them. All right, so if I had given you a vector when we were doing the geometric vectors, and I told you, hey, the magnitude is going to be 8 centimeters or 8 units, whatever it is. The magnitude was going to be 8, and it was going to go at 170 degrees. And you'd have to draw that out. Okay, now what I want you to do is I want to take that geometric vector and I want you to turn it into component form just using our formula. Here we go. I'm going to take the magnitude, which they gave me was 8, times the cosine of 170 degrees, and that's going to be your horizontal component. And then I'll do it again, 8 times the sine of 170, and that's going to be your vertical component. So let's go to our calculator. Since those are not unit circle things, we'll take 8 times the cosine of 170, and I have a negative 7.88. And then I'm going to take 8 times the sine of 170, and I get 1.39. And that's that vector in component form. And just for fun, I'm going to sketch that and see if that makes sense. Left 7, up 1, it's somewhere like right here. Does that look reasonable for a magnitude of 8 at 170 degrees? Yep, that would be right at 170 degrees. Great. Now, what we can start doing then is start combining these vectors. Remember how we had to add them or subtract them or multiply them by something? We could start doing that very quickly and get more accurate answers than what we were getting necessarily drawing it out with a protractor. All right, let's try just using this formula, getting around doing different things with that. This one says, find the direction of this vector. Well, the direction, over 3 down 2, okay, so somewhere here. Now, I know that it's a fourth quadrant angle, but we're doing math here. We're not doing bearings. It's not a ship. It's not a plane. So I am talking directional angle, talking about what would that angle or that direction be. So I'm guessing it's somewhere around a 340 or something like that, but I want to know exactly. Here's how we can find that. This right here should be equal to this right here. This here should be equal to this. So I could do either thing here. I could say 3 is going to be equal to the magnitude of the vector. Well, I can find the magnitude, and we kind of do enough of this that we probably can start doing a little bit of this in our head. The magnitude of vector v would be the square root of what? Well, that'd be a 9 plus a 4, square root of 13. Okay, so square root of 13 cosine of theta, and then I would go solve for theta. Likewise, I could do the vertical component. I could say -2 should be equal to the square root of 13 times the sine of theta, and I could solve for theta. Now, I don't really want to have to do both of them. Theta is theta. It doesn't matter. I should get the same answer both times. I'm really only going to choose one of these to do. Now, for this very first time, though, I want to show you what happens. If you divide by that, so I'm going to take in my calculator. I'm going to do 3 divided by the square root of 13. And then that's going to be the cosine of theta. So I'm going to do second cosine, second answer. And I have theta to equal 33.69. And normally I'd be happy and I'd be content, except that when I look at my picture over here, that is not a 33-degree angle. I thought it was going to be like a 340. Let me try again. Let's do this one. I'm going to do -2. I'm going to divide it by the square root of 13. But that's going to be the sine of theta, and I want to know theta, so I'm going to do second sine, second answer. And this time, I get theta to be a -33.69. I like that better. A -33-degree angle would be this angle right here. So tell me, why am I getting different answers? Well, hopefully you kind of remember, because this was an issue for us when we did law of cosines. When you type in your calculator second cosine or second sine, when you're doing that inverse, we only pull from 2 quadrants. When we do cosine, so on the cosine, you're going to want to use that anytime you need angles in these 2 quadrants. But for inverse sine, it pulls from these 2 quadrants. There was no way that doing this right here was ever going to get me an angle in the 4th quadrant. Now, that kind of helps me if I'm going to do anything in the 1st quadrant. I could do either this part or I could do this. I'm only going to do one. I'm not going to do both. If it's in the 1st quadrant, and so I can look at the ordered pair, I can look at the vector and decide what quadrant it's in. I can do either method. If I want a 2nd quadrant angle, I'm going to be doing cosine, because I know it will pull from there. If I want a 4th quadrant angle, I'm going to be using sine. Now, actually, I'm going to be a little bit picky. I probably will have you go ahead and take this negative angle and turn it into a positive angle. So you just add 360 to your answer, and you're going to be back where you want it to be. I'm going to write it actually as a 326.3 degree angle. And that's going to be my official answer. Now, what do you think you're going to have to do if it ends up being third quadrant? Because neither one of them is going to give you an answer there. Let's try another one of these problems. Same problem, but notice that it's going to end up being a third quadrant problem. Let's try this out. I always like to start with a little sketch so I understand what's going on visually. The component form is -7, -1, so it's going to look something like this. And I want to find the actual direction as an angle measurement, and I want to find the magnitude. Well, the magnitude is easy, plus I need it to find the direction. Let's go find the magnitude first. The magnitude of angle V is the square root of 49 plus 1, that's going to end up the square root of 50, which again I could simplify, but I'm going to hold off on simplifying that right now. Let's go ahead and work on the direction. Since this is in the third quadrant, neither sine nor cosine is going to work awesomely here. I actually would like to try it with both of those, and then we're going to have to do a little bit of thinking on it to see what our actual true answer is supposed to be. I'm going to take the horizontal component, and I'm going to set it equal to the magnitude times the cosine of theta. And then I'm just going to do -7, and this is why I kind of wanted to leave it a square root of 50. It's a little bit easier to do the division if I go ahead and leave it as a square root of 50. So -7 divided by the square root of 50, press enter, and then do second cosine second answer. I get theta to be 171.87. Now let's go look at your picture. Does that look like a 171 degree angle? Hope you're saying no, because 170 would stop above the x-axis, and I'm down here. That is not a third quadrant angle. Let's try again. Let's do it with sine. Take the vertical component, set it equal to the magnitude times the sine of theta. I'm going to take -1, divide it by square root of 50, and then do second sine, second answer. I got theta to equal a -8.13. Well, think about where a -8 degree angle is. That's somewhere right here. That's not the right one either. Neither one of these is the correct answer. But because of all the symmetry that is involved, we can figure out what the angle is. If you look at this angle right here, and really what you're finding is you're saying when was the cosine that, what was it, a 0.9899 is what I have in my calculator, or it was negative. When is cosine negative 0.9899? Well, according to this, that happens, well, you know what, I'm going to redraw this. The 171.87 happens right here. And the cosine value, because your cosine is your x, it's really telling me when is that going to be over that far right there. Well, it would happen there, but wouldn't it also happen down here? My x value would still be that negative 0.9899 number down there. Because of the symmetry, what that would mean is that this angle, this little angle here, would have to be the same as this little angle right here. And if I could find some kind of a little angle measurement there, I could figure this out. All right, I think I'm going to do that. If I know that this is 171.87, couldn't I just take 360 and subtract 171.87, and it would catch me the actual angle that I want? I'm going to try that. 360, and I'm going to subtract 171.87. All right. I think what I have found is this actual angle, which is in this problem, the one that I really want down here, is a 188.13 degree angle. Now, I'm going to look at the sine version of it over here, and let's see if we can, let's see what we get. Hopefully, I end up with this 188 again, because I don't want to get two different answers. I'm going to draw it out. The angle that I got as an answer was a negative 8.13. All right. That's not really the angle I want. I want the angle that's over here. And if you think about it, on this one I was doing the inverse sine, and I was getting my sine value to be negative 0.14. Right here at this particular spot, at this angle, my sine value, the y value, I'm down negative 0.141. Okay, and I'm just looking at my calculator to look back at that number. Where else would I be down that much? Well, it would happen over here also. I would be down the negative 0.141, which means this angle right here is symmetrical with this one here. These two little angles would have to be the same. Well, I know what that angle is. It's the 8.13, which means this is also 8.13. And since this is the true angle that I want, if this is 8.13, I could go 180 plus 8.13, and that would get me the true angle that I want right here. Well, that's just 188.13. Look, I got the same thing either way. You're only going to do one of these. You don't need to do both. You don't need to get this answer twice. You have to choose a method because neither one gave you the right answer the first time. You need to choose a method and then, or choose a sine or a cosine, go that route, and then just look at the symmetry that's involved and figure out what your true angle is. Now this is only third quadrant angles. I wanted to do at least one of these. Not every angle is this complex. Remember, if your angle happens to be in either of these quadrants, you're just going to do the cosine version. If your angle happens to be in these two quadrants, you're going to do just the sine version. If it's the first quadrant, you get a pick. It doesn't matter. You do the same thing. If it's a third quadrant angle, that's the one you got to look at, choose a method, do some symmetry stuff, math it out. Here's where we pull it all together and we take everything that we've done with vectors and we put it into one big old problem. So this is where it gets fun. Big star, this is an important problem. Several steps involved. We have an airplane. It's flying on a compass heading, which is a way of saying a bearing, of 340 degrees, 325 miles per hour. So there's your direction and your magnitude of your vector. However, we have a wind that's blowing with a bearing of 320 degrees at 40 miles per hour. We have two parts that says find the component form of the velocity of the airplane and find the actual ground speed and direction of the plane. So we're going to take this information, turn it into a component form of a resultant vector, and actually convert that to actual ground speed and direction of that airplane. Okay, very applicable type of problem here because you have this airplane. Now let's talk about what's going on with this airplane. It's going at 340 degrees with a bearing. So I'm going to call this like my vector P here. And I'm going to draw this out. This airplane is going a bearing of 340. Remember, bearing is due north, going clockwise, 340 degrees. That's almost all the way around. It's just shy of all the way around by about 20, well, exactly 20 degrees. So there's my plane vector right there. Now I'm going to have to do some math with that. I need to take that plane vector, that 340 degrees, and I'm going to convert that to a directional angle. So as a directional angle, that's your 90 plus that extra 20 that we said that was going to be. That's 110 degrees. This vector P that I've drawn represents basically what the pilot has the plane set to do. It's going at 340 degree bearing, which is 110 degree directional angle. and it's going 325 mile per hour. The problem is there's a wind that's going to blow it off course, and that's not really what the plane is going to do. We have a wind, and we're going to draw this kind of like a geometric vector, where at the tip of that one is going to be the tail of my wind vector. Now my wind vector has a bearing of 320, so that's a little less than what my plane is doing. So it's going to look more like this kind of thing. And it's going to be much, much shorter because it's only going 40 mile per hour, and that represents your magnitude. In the end, though, it kind of helps my plane, and my resultant goes from here to here. And ultimately, that's what I'm shooting for, is what is the plane really doing? What is the resultant going to be? Now, we're not going to draw this out like we did with a protractor and such with geometric vectors. We're now going to finally use all this algebra that we've spent a couple days learning to be able to solve that problem algebraically. It looks like it's just a problem where you take your plane vector and you add your wind vector, and that's how you get your resultant. And that's exactly what we want to do. Now there's one thing that we have to do before we get too far, and that is to change this 320 in the same way that we turned the 340 into 110. What do you think a 320 would be as a directional angle? And I'll just sketch this real quick. This was our 320, right? That would be 320 if you're doing bearings, because there's 90, 180, 270, and a little bit more, right, to get to the 340. What would that be this way? Well, if this is 340, I'm sorry, let me say that again, 320 is what I'm converting. So a 320 would be 40 degrees shy of all the way around. So this angle right here is going to be 40 plus the 90. Looks like I'm looking at a 130 degree angle. Those are the two angles that I'm going to use as I do the math. Okay, let's come over to this side. I'm trying to write little because this is a big problem. I want to take my plane vector and I want to add to it my wind vector. And when I add the two vectors together, I'm going to have my resultant vector. And that's what I want. The trick now is to write the plane vector like we learned how to write vectors using the information they give us, but we can write it in component form. We just throw the math in there as the component form. It's going to be the magnitude of the plane times the cosine of my directional angle. The magnitude of the plane was its speed, 325, times the cosine of the directional angle, 110. 325 sine 110. Now let's do that with the wind vector. The wind vector has a magnitude of 40. Cosine of the directional angle 130, and then 40 sine of 130. This right here is what I actually want to see. You don't have to give me all the decimals. I really just want to see how you're setting it up, because I can usually find your errors in how you set it up. Then we just add. You add your horizontal components, you add your vertical components. In my calculator that I'm taking 325 times the cosine of 110, and press enter, and I'm going to add to that 40 times the cosine of 130. I end up with and let's change this to pink here, so this is my resultant. It is going to be negative 136.86. That's my horizontal component. Kind of makes sense because for my resultant here, I am left, so the horizontal component should be negative. Now let's try it with adding the vertical components. 325 times the sine of 110. And then I'm going to add to that 40 times the sine of 130. This time my vertical component is a positive value, which makes sense because it is up. Oops, 336.04. And that represents this resultant vector in component form. We've done part A. Find the component form of the velocity of the airplane. So let's go ahead and box that in. That's the first answer. The second part, it says find the actual ground speed and the direction of the plane. Well, the actual ground speed is this speed measurement that is our magnitude. We need to find the magnitude of our new angle. I'm sorry, of our new vector. Well, we can do that. The magnitude is just going to be the square root of the negative 136.86 squared plus the 336.04 squared. Let me type that in. So I square root that, and my magnitude of my resultant is 362.84. Now that's a magnitude, that's in miles per hour. Now let's look at if that would make sense. Remember, the original airplane was going 325, but that wind was going enough in the same direction that it actually was kind of helping it and ended up increasing its speed to 362. Now it didn't increase it by 40, that would have been 365 if it was going in the exact same direction, if the wind was pushing it directly, but it did increase it a lot. All right, we've got our actual ground speed, and the last part is to find the direction of the airplane. The direction of the airplane goes back to what we did on that previous example where we were looking for theta. Now, I can either use this value or I can use this value. It depends on if I want to use inverse cosine or if I want to use inverse sine. Since I'm in the second quadrant, I should be doing inverse cosine. I'm going to choose to use my horizontal component, and I'm going to set up a little equation here. So the second part of this then, I'm going to take that horizontal component, negative 136.86, and that should end up equaling this right here, the magnitude times the cosine of theta. Well, the magnitude I just found, I had to actually find that first before I could find the direction. This is the magnitude. I'm working everything with the resultant at this point. The magnitude is 362.84 times the cosine of theta. Let's divide by the 362. And then we'll have to do inverse cosine on it. All right, so I get a negative 0.377, but I have to do second cosine, second answer, and my theta ends up being 112 degrees. Which makes sense for this particular problem because my original plane was 110, but the wind is pushing it a little bit this way, which makes my resultant actually be 112 degrees. That makes sense. I like that. I want it to make sense as we keep going. That's why I drew this picture out. However, I don't really want to answer as a directional angle. They gave it to me in bearings. I need to be answering back in bearings. I have to turn that into a bearing. And I put 112. I need to probably be a little bit more exact than that. Oops, that is not what I wanted. I don't think it's going to let me erase that. No. So it's actually a 112.16. So I'm going to squeeze that in. It's 112.16 degrees. Now I have to turn that into a bearing. So let's think about that. I'm going to use the picture that I have up here. If this is 112.16, how could I turn that into a bearing measurement that goes this way? Different ways to do it. I'm going to do it a little bit differently than I have in the past. I've been always using this little gap space here, but we can also use this little gap space here. Let's try doing it that way. You just have to understand the symmetry and the values on your unit circles for this to make sense. But I know it's going to be 90, 180, 270, but I need to know this little bit to add to that 270. Well, if this is 112.16, couldn't I just take 180 and subtract that? And that would leave me with that open space. That's what I'm going to do. I'm going to subtract it from 180. And I end up with a 67.84 for this gap space in here, 67.84. Now, I'm going to add that to the 270 that's wrapping around. There's your 270. And I get 337.84. And that is the bearing. And that's the actual direction that I would report, which is the direction of the airplane. So much stuff involved here. Look through this, watch this part of this video, this slide again if you need to. We'll have several of these that we're going to work on in the next couple days. So good luck.